I guess I'm going to look at how to build a vector search app in a local context. And this is going to be useful for building out applications that might exist on the edge. And so the idea here is to look at how you can take some open source projects and then create something that will have pretty decent performance and get good results without having to use external APIs or things like that that might be actually slower and actually add a lot of overhead that you don't necessarily need. So this is mostly focused on one, how to build a vector search app, but two, how to do it in a very efficient manner so you can get a high-speed vector search without having to spend a lot of money or use a lot of compute resources. So let's talk about how a vector database works. In theory, they're pretty straightforward and what they're trying to accomplish. But if you were to look at the data in a vector database, it would just be a bunch of numbers. And it's not as intuitive as something like a table in an RDBMS. But once you kind of understand how a vector database actually works, then it will be a little bit easier to understand what all those numbers represent. Now, at the core, a vector database is really about just trying to represent the data in the database by grouping things close together. And the way it groups them close together is using dimensions. So we typically think in 3 dimensions. So we have width, which is on this axis right here, and that's typically represented with an X. We have height, or the vertical axis, which is typically represented by a Y, and then we have the depth axis, which is typically represented by a Z. So we have 3 dimensions in this particular representation. So if I wanted to search in this particular database, what I'm going to be looking for are things that are similar to one another based on their relative location for my query. So if I say, give me something that looks like a bean, well, it's going to use the data that represents a bean, that is the vector data that represents the bean, to find the bean portion of this particular database. And so it's going to say, well, a bean has these particular coordinates. It's going to have an X, a Y, and a Z coordinate to it. And using those 3 coordinates, I can then locate within this vector database where that bean might be located. But the bean itself is closely related to other items as well, like peas and lentils. And so based on this search, the search is obviously going to return beans, but it's going to look for things that are closely related to beans based on their relative proximity to what you're actually searching for, which in this case would be kind of everything in this circle right here, which would actually be a sphere in 3 dimensions. However, if I wanted to search for something that's a little bit less specific, say I want leafy vegetables. Well, leafy vegetables is not represented in the data here. I don't see leafy vegetables. There's not a key word for that. But if I was to search for that in the vector database, that's going to basically land it somewhere around this section right here. And in this case, if I search for leafy vegetables, I might get a coordinate that's maybe up here somewhere. But if I do a search in the proximity of this for things that are closely related to it, I will get things like lettuce and kale. And that's what I would get back in my search results. And similar, if I was searching for something like pasta, if I search for that in my vector database, I'm probably going to get things that are related to pasta, which is going to be maybe a vector right here, but I'm going to do analysis to figure out what's closely related to it. And therefore, I'm going to get these results in my search results. So all of this is to say that a vector database is more about searching for things that are closely related in concept or in meaning to what I'm actually looking for. Now, I can use keywords, certainly, but it's not always about the keywords that matter here. It's more about the meaning of what I'm searching for than anything else. And that's really where the LLM comes in. And we're going to talk about how that works in just a second. But understanding this concept is critical to understanding what an LLM is actually going to contribute to your vector searches. So with that in mind, we're going to talk about now how to get data into a vector database. Now, it really all starts with documents. Now, the documents that we have can be anything. It can be PDF. It could be a Word document. That's with text documents. But you can also do vector searches on things like images or videos or sound files. It really doesn't matter. If you can vectorize it, you can put it in a vector database. But vectored searches on text are one of the major use cases because a lot of folks have these large document repositories, but they want to be able to search on these and get meaningful searches out of those without having to know all the keywords. And that's really the power of a vector search. But let's talk about how we go from a document to a vector database though. Now, once we have our document, we're going to basically pass that document into some kind of ingestion algorithm. Now, it could be an API, it could be a script. It doesn't really matter. They all kind of work the same. But the ingestion portion of this basically takes the document and extracts the text from the document. It basically removes all the formatting from it. If it was a Word document, it removes the word formatting. If it's HTML, it removes the markup. If it was just a PDF, it removes all the PDF stuff, and it just gets the raw text that's embedded in that document. And then it does a process of tokenization on that particular text. Now, tokenization is taking the raw text and breaking it up into smaller chunks. Now, the chunk itself could be a word, it could be a combination of words, it could be a punctuation. At the end of the day, tokenization is just basically trying to take the text itself and break it up into small enough pieces that we can then take that and assign a number to that particular token. Because an LLM can't understand raw text. It can understand numbers, but it can't understand raw text. So by using a tokenization algorithm, you're taking the raw text, breaking it up into smaller chunks, and then assigning a number to that particular chunk. And then you're taking the numbers themselves, and that's what gets passed into the LLM. Now, the LLM will then take that set of numbers and apply the embedded logic in the LLM to that numbers to return some kind of result. But that LLM itself was trained on large data sets. It's got tons and tons of semantic meaning baked into the LLM because that's what it's trying to do. That's ultimately what an LLM is attempting to understand is when you pass in a particular set of values, it's trying to infer from that set of values what your intent is. It's trying to infer or predict what the output that you're looking for will be. And by training the LLM on thousands and thousands of documents, it learns the patterns that it needs to infer whenever you pass in a particular query or a particular document. And then that's what it's going to return back to the ingestion algorithm is based on the input. What am I going to pass back as output that's going to be a representation of what the LLM thinks is the semantic meaning behind that particular text. Now, with that set of return values, now we have something that we can store, and that's what actually gets put into our vector databases because the LLM itself is really just returning a set of numbers back to you. And those numbers are the vectors that we then put into our vector database and that we can search on. So by doing that particular ingestion algorithm, we're basically just taking the raw text, vectorizing it, and then sticking it into a vector database that we can later search. So now that we've talked about how to get data into the vector database, let's talk about how to search it. Now, the search itself is going to start with some kind of query. So this could be a statement, it could be a question, it could be a list of keywords. The way that you shape that will have implications on the way that you get data back. But by and large, the most important thing to put into the query is a context that is rich with things that are going to provide meaning. And so if I'm talking about farming kale, I'm going to put in some kind of query that talks about farming kale. I'm going to talk about, I want to know how to grow kale in the Southeast United States between the months of March and August. And that's going to provide me geographic data. It's going to provide me a particular context about what I'm looking for, such as farming, a particular kind of vegetable, and the kind of conditions that I'm going to be looking for, and all these different things that are related to that kind of query. And so that's what I'm going to put in there. Now I can phrase that just as keywords, a question, or a statement. That can change the way that the LLM interprets it. But at the end of the day, it's mostly about those semantically rich words and context that's going to make this actually perform rather well. So with that, I'm going to then pass that to an API. Typically, a search is going to be done through some kind of API, but it doesn't have to be. You can use a search just on an embedded script or something like that. And like the ingestion side, it's going to take that query and it's going to vectorize it. It's going to break it down into a set of tokens. It's going to then convert those tokens into numbers, and then it's going to pass that query back to the same LLM that I use to ingest my documents with. That's important because if you used a different LLM, you're going to get a different set of vectors back from the LLM, and it's not going to have any kind of relevance to what's in your vector database. So you have to be able to use the same LLM that you ingest your documents with for whenever you're querying your documents. So in this case, whatever I query against is also going to be the same thing that I am ingesting my documents with. So I'm going to again pass that tokenized version of my query into the LLM, and I'm going to get back a set of vectors. Now, this is where the real magic happens. I'm going to take that set of vectors, and then I'm going to do a vector search on my vector database. The LLM itself doesn't do the vector search. It's the part of the process that translates the raw text into something that it thinks is meaningful, and it's represented by a set of vectors. That's basically just a list of numbers. And then the API takes that and passes that returned set of numbers from the LLM into the vector database, and it performs what they call a vector search on that database. Now, the vector search basically is looking for something that is close in the space that it's representing to that particular set of vectors that you're passing in. And there's a lot of different algorithms that they can use for this. One of the simple ones is just using Cartesian mapping, which is basically where you have the Cartesian space around your particular vector looking for things that would be included. And that could be represented as, you know, a sphere in 3 dimensions or a cube or however you want to represent that. And it's looking for things that are relatively close in terms of Cartesian matching. And there's other algorithms that folks have developed for doing vector searches as well. But in any case, once the vector search runs, now it's finding the matches in the database that have similar semantic meaning. And that's what gets returned back to the API. And then the API just simply relays the results back to whoever called the particular search with that set of documents or some kind of referent to that document. In any case, it doesn't necessarily store the documents in the vector database, but it gives you some way that you can then look for that document, maybe on a file share or in a document database somewhere, or some kind of keyword that might be associated with it, or URL, whatever it might be. But it's some way to get that document that you're actually looking for that's represented in the vector database. In any case, the API then is returning that back, and then the user will then see the results and then can respond to those results however he or she wills. And that could be through maybe refining the search, or maybe they go and read the results, or whatever it might be. But at the end of the day, they've got something that is representative of the actual search they passed in based on semantic value, not necessarily based on keywords or anything like that. So for our purposes, we're going to be working with 2 different pieces of tech here that are kind of essential to this. And there's, of course, some supporting technology around this. But one of these is DistilBERT, which is based off of BERT, which is an LLM that was developed by Google. But this particular version of this LLM is a distilled version of it. Basically, what it did is it took the original BERT and distilled it by reducing the number of parameters in the model. That's basically the number of data points that are represented in the model, and made some other optimizations to it to make a smaller version of it that retains the accuracy of the original LLM, but improves the performance and the overall memory required to run it. So DistilBERT is very useful for what we might call edge cases, where we have an LLM running on the edge, where you have data coming in off of things like IoT devices, for instance, or something like that. And you need to process data very quickly in an environment that doesn't have a lot of compute resources. So something like DistilBERT is an excellent model for that. Now, for our vector database, we're going to be using a vector database called Milvus. Now, there are certainly other vector databases out there. There's also vector APIs and searches for many popular databases as well. But Milvus is a kind of a standalone database that can run as a single node or as a cluster. But as a single node, it's going to work for what we're going to be doing. But you can set up these clusters of Milvus, and it's a high performance vector databases. And you can put potentially millions of different vector documents into this database, and it will index those and then be able to search on that database with sub-millisecond speed. So it's really, really fast. Between these two, you get a high performance search going on with these particular open source technologies. Using something like ChatGPT or a similar approach would take exponentially longer because the LLMs are much larger, and it also takes a lot more effort to actually process the documents and the search requests using a larger LLM. So by using a smaller LLM and a localized search database for our vectors, we can improve our performance drastically in this particular context. So that's the technology stack, but let's look at how to implement this using Python and just some of the pieces that it involves. So the first thing that we're going to do to show you all this, I'm going to show you the environment and then the dependencies, and we're going to look at some code and show you how to start this all up. The first thing we're going to do is install the database server, which is pretty simple to do. It's all based on Python, so we're going to be working on the Python ecosystem, and I'm going to be using a Linux context. So you can get Linux context on Mac, Windows, or just a standalone Linux box. And I'm using Ubuntu for this particular instance for the distro. So once you've installed Python, the next thing you need to do is just install Milvus, which is pip install Milvus, and you can use PyPy to install that package, and everything is installed there. Now it's going to install it in this directory right here, and you want to go poke through that. So cd into that directory, it's in your home folder, and you can just type in Milvus server and start it up, and this is going to start the server running. Now Milvus itself is the particular version here is Milvus Lite, which is what we're going to be using for our database. But once it's up and running, we can now open up a new tab and get WSL, and then we're inside of a new context, but we're just going to leave Milvus running in that other tab. So once you're up and running, we're ready to go and install all our other dependencies. So this is the code, and you can see here are my dependencies. I'm going to need pandas, I'm going to need transformers, torch, and Milvus. And then for the API, which we'll look at this more in detail, I'm just going to need Flask. And so to install those, you can simply use the CLI to install a lot of this. So I've got the same folder up here with all these files in it, and it can just do pip install on all of those particular packages. And I've already got all these installed, so mine are going to go really quickly. If I do Milvus and transformers, you can see that these are already satisfied, so I'm not going to get anything. The transformers is an important one because that's where we're going to get our DistilBERT transformer. And then if we don't have Torch installed, we can install Torch. Now, Torch and transformers can take a while to run. And also a note, the first time that you run this, you're going to get a download. And it's going to download the models associated with this. So it's going to download DistilBERT. That's a one-time only thing. So once you start the model download, you only have to download it once, and then thereafter it's installed and you don't have to worry about it. So that's pretty much it for the dependencies. Now, of course, you could put these into requirements.txt and then just use that. I'm not doing that. I just did it more manually to show you what I was actually installing. So once you have everything ready to go in terms of dependencies, now we can actually import some data. And I'm going to walk through that code first, then I'm going to show you the API code and run that. So let's walk through the import code real fast here. So the import code is the process like we talked about, where we take the raw text data and then we import it into the database here. So I'm going to be using a tokenizer for DistilBERT, and you can see that I'm loading that up here, and I'm loading a model up right here. And that is where I'm going to be using the conversion into tokens and taking the tokens and putting them into the model. And that's done by this method right here, which we'll get to that in just a second. But to kind of unpack what's going on below this, this really starts right here. And this is where it connects to the database that we just started. And then it's defining the schema for the database. Now the schema for this is using two fields that are significant for just the search. And that's this ID field, which is kind of like the primary key. And this is the embedding field. This is where it's going to store the vector database. And notice that it has 768 dimensions attached to it. Now, other vector databases will have more, others will have less. Depends on how many you need for your context. 768 is fine for this use case. Now, this is the actual metadata that's associated with this. And that's coming from a particular file that I have right here. I'm going to show you what this data looks like. So this is using Jeopardy data from shows past Jeopardy airings, where it has when the show aired, the round, Jeopardy, Double Jeopardy, and so on, category, the value, and then the question, and then the answer. And so that's the data that I'm going to be importing it. And what I'm going to be searching on is the category, the question, and the answer. So that's my import. So I'm just storing the metadata with this so that I can display that as well. Now, if you had a larger document, you probably would not store the document in this particular database. You would have something like a document database forward, or just some kind of file share wherever you're putting those documents, but you would have some kind of pointer to it. And that's where these meta fields come in right here. So the one that's going to get searched though is this embeddings field. And we'll talk about how that gets populated here in a minute. So that creates the schema. And then it comes down here and it actually just starts doing the population of this. And this is just batching everything up using 100 records at a time. That's just an arbitrary number I chose. And it's batching it up based on the record number count and then building some of the text for the embedding right here. It's just basically adding another field to the data that loaded from the CSV right here. And from that, it is then taking that 100 records at a time, and then it's getting the embedding for it right here. Then it's calling that embedding method up top. Now the embedding method right here is where it does the tokenization that I talked about, and then it gets the actual vector data for it. So the tokenization happens with a tokenizer. And so it's passing the text data into the tokenizer. And then the tokenizer then returns a set of inputs. And the inputs are what get passed into the model. And the model you can see is right here. And then that's where it's actually calling DistilBERT and then getting the outputs. And the outputs are the vectorized version after it's been processed by the LLM that I'm actually going to store in my database. So you can see that tokenizer works. It gets some outputs, and then that's where we can go back down here and start populating the database. And so it's basically just populating the values there, and then it's assigning the vectorized version of whatever the text I would want to search on in that embeddings field. And then it sets up some entities according to the schema that we just looked at, and then it does an insert on that set of records. And then it repeats that until the loop is done, which for this particular data set on my machine, it took a while. I think I have 200,000 plus records in that, and it took about 20 minutes or 30 minutes to finish that import process. Now, the next thing that it does is just defines an index. So we need an index on that so that the searches will perform better. And it's just using an index using IVF flat, which is one of the different kinds of indexes that you can use in Milvus. There's other ones I'm not exactly sure how they all work, but there's explanations for all of them in the documentation for Milvus if you're interested in reading about that. But this is just kind of a good default if you're interested in using Milvus. Now you create the index parameters, then it indexes the data, and then it just has output here. Indexing on embedding is done, and then the documents are ready for searching. So I'm doing this as a batch. Now, if you wanted to build an API, you could do an API and then insert these one at a time using an API and get the similar results of what I have here, but you would basically do the exact same thing. You don't necessarily have to define the schema and you don't have to define the index, but you do have to do the tokenization and insertion of records based on the model that you're using here. So all that to say is that's how the import process works. So let's go and look at the API. So the API is going to follow a very similar pattern to what we just looked at, and it's going to be using the same basic process. So in this case, I'm getting a connection to the database. I'm getting my tokenizer and model right here, and I'm getting my get embedding, same method that I used on the other import algorithm to basically tokenize and then vectorize what I have inside of whatever I'm getting for my search. So this one, I'm just defining an endpoint at search right here. And it's going to get fields from a parameter called query, and then it's going to get the embeddings, and then it's going to get the embeddings to list. And this is basically calling the algorithm up here that then tokenizes it, then gets the tokens, passes them into the model, then gets back the results, which then I take and then do a query embeddings, and that's basically where I'm taking the output from that and then setting up a query. From that, then I'm setting up my search parameters right here and telling it how many I want back. And then this right here is saying search the database. So this is calling the database to search it. And this is then telling it the query, the embedding parameters, which I have passed in up right here. And then it's telling it which field to search on. And here's the search parameters right there. I want 10 results back, limit to 10. And then these are the output fields that I'm interested in. Now, I probably wouldn't include the embeddings per se if I was going to be returning this. But if you want to see what that looks like, it's just a bunch of numbers. But the metadata associated with this is certainly the stuff that I'm probably going to be most interested in, because that's the stuff that as a human I can read fairly easily. And then this is just taking everything and then formatting it in a form that I can then return as an object, and then it returns that as JSON data. And so it's going to return the distance, which is the relevance score. That's like how close is this result to whatever I'm interested in. And then it's going to say show number, the date it aired, the round, the category, question, and answer. So that's the search. Very similar to the importation. It's just instead of doing a document and storing it, it's taking my search and then tokenizing it and then passing it to the LLM, getting back to the vectors, and then doing a search against the vector database from the output. And then I get back answers based on what I put in for my search. So let's fire this up and see it in action. So to start this up, I'm going to come over here to my directory, and I'm going to do ls to show you that I'm in that directory. And then I'm just going to do Python 3 and do search API. And that's going to start the app on this one right here. And this is the endpoint that I'm going to be interested in right here. So I'm going to use this endpoint, but I'm going to use Postman to query this guy. So once I have it started, I'm going to pull up Postman and put in some queries into this particular database. Now, the way that this works is pretty straightforward. Now, let me pull up Postman onto the screen so you can see what I'm doing here. Pull this over here. Okay, so I have my endpoint, and that's based on what I put into the Flask app. And then I have a query right here. And so this is my query, and it says, can you give me all the questions related to Spock and Star Trek? And so that's the query that it's going to process. So I'm going to send that over, and let's see what it does. It gave me a bunch of questions: Deep Space Nine, Battlestar Galactica, letters and numbers about Star Wars, Zachary Quinton, Star Trek. This is some Ramsey and Travers. This is some kind of sci-fi show, extraterrestrial. So it's basically looking for, it's doing some semantic matching based on science fiction. That's what it's trying to interpret this as. So Spock and Star Trek would kind of give me back things related to science fiction and questions related to that. So that's one way to query this. So none of these necessarily mention Spock, but they do. Some of them do mention Star Trek. Some of them don't, but they are related in the fact that they are science fiction shows. Can you give me all the questions related to farming kale or something like that? Let's just see if this returns any kind of results. And this is talking about farming right here. Some more farming, native. This is talking about birds and things like that. So it's thinking about nature, menageries. Okay, so not a whole lot about farming kale, but it did have some questions about Star Trek. Let's see if I can do some Star Wars here. See what that does. And this is giving things about R2-D2, which would be about that. Another one about Deep Space Nine, so Star Trek related to that science fiction theme and so on. So this is able to return some things that are semantically related to what I'm actually looking for. So you can see the results there are in keeping with the spirit of what I'm looking for in terms of searches. Now, given that I didn't really put a lot of effort in fine tuning this to make it return even better results, I am surprised at how well it did work, because this is just using some unmodified models and just using the unmodified model to try to determine semantic searches, and then also getting back results that are in the same vein of what I'm kind of looking for. So interesting results there. So if you're interested in building vector databases that return things rather quickly, this is certainly a way to do it. And you can see here the response time was 25 milliseconds, so very fast as well. If you're interested in doing vector searches and getting back results that are relevant, but also doing it very quickly using something like open source software and distilled models and standalone databases, what have you. So I hope this has been informative to show you how vector databases work and how vector searches work, and showing you some tooling that you can run on a CPU without the need of a GPU or anything like that, and get back pretty surprisingly fast results using vector searches and vector databases in a local context. So certainly something you might want to check out if you're interested in this kind of thing. And there's of course 1,000 other ways to do this, but this approach is very accessible to pretty much anybody that has a computer. And if you want to learn how to do this, follow along with this, and I'll make this code available on GitHub, and I'll link that in the video description down below. And as always, thanks for watching, and look forward to more videos on Tech on Fire with Blaze.
If you like this content, please consider subscribing to the channel by clicking on the subscribe button. You can also like this content by clicking on the thumbs up, or share this content with your friends, and also comment in the comment section down below. You can also find me online at www.blaze.net or on Twitter at @TheOneMule. And as always, thanks for watching.